So again, we are, I guess today is probably the last class about Tikhonov regularization. It's one of the principles that we consider. Is the idea when you have a data, you have an hypothesis space, for us always a reproducing kernel-based space, and you minimize the error plus some penalty term, which is the square norm, because that's what we're going to start from. And we basically, in our menu, there are 4 things. The first is the representer theorem, which is a general result about a property of the minimizer, the estimator given by this algorithm for all different loss functions. And then we actually turn this result into to specialize to specific loss functions. So last time we introduced logistic loss function that gives rise to the algorithm typically called logistic regression. We then started discussing, although we didn't completely finish, the hinge loss, so I would like to finish today. And then we're going to do 2 least squares. I think you can steal chairs from outside and bring them in rather than stay standing up. And there's room here in the front. They're not supposed to be so many by now. So it's not my fault. OK, so let me summarize. I already wrote the stuff that we already said, so just to put some order, OK? So this is the function we want to minimize. This is the representer theorem. In essence, it tells us that something somewhat magical happened. Even though we work in an infinite dimensional space, by the time we look at the data, we're always dealing with finitely many parameters. Because the solution can be written as a linear combination of the kernels at the training set points, not on any point, just the training set points with a number of coefficients, which is at most the number of points. Okay? Now, this result is somewhat very instructive from a conceptual point of view. It doesn't lead us all the way down to an algorithm because we still have to compute the coefficients C. And we might have different ways of doing that. It's his fault. So what I was saying is that this is not, it's not exactly an algorithm because we still have to figure out how to compute the coefficient C's. And this will depend on the loss function to be considered. It turns out that different loss functions typically give rise to things that we call with different names. The logistic loss function gives rise to what we call logistic regression, which is exactly this specific choice, okay? Which is, by the way, a classification algorithm and not a regression algorithm. And so what we did last time is that we considered this loss function, and we actually said, OK, let's try to see how we can solve the problem for this loss function, how we can actually find the solution. Rather than starting with this expression, we started from the linear case. What do I mean? That we assume for a minute the function to be linear, and we actually applied gradient descent. Why did we apply gradient descent? Well, everything is smooth, and in fact, we have a nice function. It's strongly convex. The dependence of W through the loss function is nonlinear. So if you just try to check the optimality condition, they don't give rise to a nice equation that you can solve. And so what you do is that you actually go through first order method. So gradient descent is the most basic example of first order method. Why first order method rather than something else? Because one can check from just looking at the form of first order method. The first order method has a very simple, each iteration is very simple. Okay, so only typically vector-vector or matrix-vector multiplication needs to be done. And so typically the cost per iteration is manageable. There are not very complicated operations to be done. It is that operation like matrix-vector multiplication can be done without having to store the whole matrix in memory. You can just, if I have a big memory A and I want to multiply by a vector B, I don't need, strictly speaking, to put all the memory A in matrix if it's big. I can look at the first few rows, do the multiplication, and throw those rows away, read some more rows. Of course, I have to spend time reading from disk, but that's good news, right? There might be other operations, like, for example, inverting the matrix, that if you just do naively, might require to just take the whole matrix in memory, okay? So the nice thing about these guys is that in principle, they scale pretty well memory. They might be slow, but they scale pretty well with memory requirements. Okay, and so what I was telling you last time, and we go this way because this is the prototype example of state-of-the-art large-scale learning algorithm, first-order method, became very popular in the last few years exactly because of the reason, because the relatively ease of implementation and relatively small memory footprint. Okay. So what we do then we just recall very briefly what is gradient descent, but this is more or less known to everybody, and then we just compute the derivative and look at it. Okay. And if I did mistakes, this is how it looks like. Again, the only thing I did is that I erased the exponential at the top and taken the bottom. This is how it looks like, and well, nothing. You just have to plug it back in, and that's your algorithm. Okay. One thing to know is that this algorithm is particularly nice because for smooth functions like this, you can actually fix a fixed step size, which depends on the second derivative of this. So you would have to go in, look at the second derivative of this. Is not a vector, it's a matrix, it's the Hessian at that point. And then you would have to find an upper bound on the norm of this matrix. Okay? It's easy to check, and you can do it as an exercise that in this case, this basically will boil down to, you can just find that this doesn't need to do any computation, at least if you have an upper bound on y and x. If you know that your x's are in a ball and your y's are in a ball, you can give an upper bound on the norm of the Hessian without actually performing any computation. And that's one other reason why this makes this algorithm somewhat efficient, because you don't have to do heavy matrix operations. Okay? All right, so this is our first algorithm. This is not quite solving the problem for the nonlinear case, but just for the linear case. How did we went after the nonlinear case? We took somewhat not perhaps the first route that one could think about, which is, okay, I know that I have this result. I'll plug it back in here, and I take gradient descent with respect to the C. This would be the obvious thing to do, right? You give me these results, I plug it back there, and I take the gradient with respect to the C. You can do that. It turns out that you get an iteration which is slightly less efficient than the one we actually provide, okay? So strictly speaking, this means I use the representer theorem, and then I apply gradient after applying the representer theorem, okay? What did we do? What we did is to actually prove a representer theorem for this iteration itself. What does it mean? Rather than proving that the minimizer satisfies this expression, we actually prove that each time we run this iteration, each w, or each function that is corresponding to this w, satisfies a representer theorem. It's written here. If you run, we actually proved it first in the linear case. We proved that the function that you can compute through this iteration can actually be written in this form. Okay, can be written as a linear combination. It's exactly a representer theorem, not for the minimizer, but for the algorithm itself. Is it clear? So we derive a new representer theorem from rather than applying one and then using gradient descent. And again, we do this because we get a slightly nicer iteration. Let's look at the iteration we get and then remind what was the proof. The iteration we get just say, okay, my function looks like this, like a representer theorem, but by reproving it, I get something for free. I actually can tell you how to compute the coefficients for the logistic loss, because everything now is specialized to that loss. And how do they look like? It's a very simple iteration. You have to choose exactly the same step size as before. You still have to do just a simple update of the coefficients. And basically, this is the simple form of the iteration. Okay? So roughly speaking, you have to take, this xi disappears from that term. You just get this. So every entry of this vector is equal to minus yi divided by this term. This is the same as this, but the good news is that now, see, in this case, I can replace ft with this expression. So nothing either here or here requires to have w, but only w multiplied by something. And so that's why we can just replace everything with a kernel. So all you need to compute this expression is ft. And ft, you can check it's fine. Okay? So this is the statement of the result. It's not the proof. The statement is, I can prove that I can always compute the solution of this. Okay, through a gradient descent procedure by considering this function where coefficients are given by this, where this term is given by this. Okay, so what you can appreciate is just stop and say, okay, that's simple enough. Okay, how did we prove it? The way we proved it is, rather than going straight on to the nonlinear case, to wait and do the linear case first. Okay, and just proving that in the that in some sense this w can be written this way. So essentially, we wanted to prove that this is actually equal to xi x t I. That's what we actually proved. We proved that this expression can be written this way. So we actually gave the proof for the linear case, and then we just do, and so first of all we considered the linear case, okay? Then what did we do? We know that this way of writing the results is equivalent to actually asking the WT. Can you see more or less? Because I know. This condition is completely equivalent to the fact that WT has to be equal to X hat transpose CT for some coefficient CT. Okay? We actually wrote this, you just have to write it down. Writing this or writing that, it's equivalent. And so that's what you want to prove. So how do you do that? How do you prove that the WT that is given by this iteration actually can be written this way all the time by induction? Okay, just a one-line induction proof. So again, going from the linear case to the nonlinear case, the way you do it is first you consider, for the sake of simplicity, the linear case. Then you realize that the result you want can be rewritten this way, and then you just prove this by induction. And then you realize that there was nothing special about, that the linear is just a matter of presentation, but there's nothing special to it. So you can actually do everything for a generic feature map and then go back to a generic kernel. Make sense? I'm cheating a little bit. This result is true for any kernel. Strictly speaking, this argument, you remember that I told you that sometimes the connection between when you use feature map, the connection between function and W's is not one-to-one. Well, this argument, strictly speaking, works in the case where it is one-to-one, okay? With a change of notation, basically it works in any case. So the final result is correct, and the basic argument works no matter what. But I would have to actually cover that case, I would have to introduce a heavier notation. So we just give you this because for those of you who are interested, I'm happy to discuss this anytime. But this basically gives you not only the result, but also the proof. And the rest will be just heavier notation. So strictly speaking, but just keep in mind that if this assumes to go smoothly in that F and W are one-to-one, okay? All right, so I think this is basically the main core of what we said about logistic loss functions. Any questions or doubts or curiosity about this while I drink because it's hot? Everything after this, everything here depends on the loss function. This is the last thing I said that doesn't depend on the loss function. Everything afterwards, the loss function. And it is for the logistic loss. No. As you see, everything here. So this is really for the linear case. Here, it's for the nonlinear case. In fact, you see everything nonlinear. It's just a trick to present you the proof in a simple way. Okay, that's all. So it's really, what you say is, I assume it's linear, I do the proof, and then I realize that I didn't really use the fact that it was linear anyway. It's fine for any feature map, and then I'm done. It's just, again, that's one of the nice things of RKHS. When you go down, as long as you understand what's going on, the fact that you have this to do this, forget about the feature map and then remember that you have it, you can just do linear algebra. And that's what we did to prove the thing there. So it became particularly easy because of that reason. That's, one might claim that we do functional analysis kind of because at some point we just do linear algebra. It's because of, okay? Of course, then you can ask, okay, what the hell am I doing? Well, you have to study the functional analysis I taught you for 2 classes to understand what's going on here. But once you understood that, you can just do that. You can just do this route and just do linear algebra kind of reasoning, okay? And again, I'm assuming you've done this already, so I spent 2 classes to tell you the stuff that probably nobody told you before. Okay. Anything else about this? Want to take a chair? I'm suffering for you guys. All right. But I'm doing the same, so I guess it's fine. So he's asking the learning rate. How do you choose the learning rate? In any case, you have to consider the, right? Now, the question is, okay, here I could just compute the Hessian of this with respect to x and see what I get. What about here? Actually, you can compute, you can show to the same Hessian. You don't need the feature map. Please take a small separate discussion, okay? Basically, well, I'm going to show you, if you remind me, like half an hour, I'm going to show you what is the trick you use. So the claim is you can compute this constant nicely, even in the nonlinear case, okay? All you need to have is a bound on the kernel instead of a bound on the data. And in, now it would just be a diversion, but in half an hour, I can just show you exactly the trick you use. It's simple, okay? Anything else? All right, so we now want to deal with this loss function. And this loss function is the one that, this plus function looks like this. So it's not differentiable, okay? So you can kind of just say, well, I'm just going to ignore this, okay? I just take some derivative. And that's what we want to do. But we also want to know that that's actually a principal thing to do. So we actually spend a bit of time understanding why just taking, say, the left derivative of that guy is actually fine. And to do that, we gave a hand-wave introduction to convex analysis in a way. We actually introduced a few definitions and a few that actually do require a proof and are not obvious, but they're acceptable. And they don't say there are other approaches where the jump in intuition is bigger. Hopefully, this jump in intuition is not too big for most of you. Okay? How did the story go? Well, I have to now I have a function, f, from Rd to R. Okay, so this is just a small convex analysis, embarrassing concept of convex analysis interlude. Okay. Take a function which is from Rd and to R. Let's say it's continuous because it doesn't really matter. And let's say it's convex, but not differentiable. So I do have some properties, but I don't have the usual property. I cannot just talk about the gradient. Can I talk about something that roughly has some of the property of the gradient? Yes. Change slightly the name, we call it the subgradient. It's a strict generalization because for the case of differentiable function, it goes back to the usual gradient. What is it? Well, I gave you already the simple introduction the other time. So let's jump into the general definition. Gradient is one vector. The subgradient is not one vector. It's a set of vectors. It's all the set of vectors that satisfy this geometric property. You stare at that and you're like, I don't know. But if you actually consider the one-dimensional case, the definition will become easier and even the geometric interpretation will become easier. Because what are you doing? You're considering all the lines that somewhat stay below the one point there. That's kind of what this equation is saying. Okay, the geometric interpretation is consider all these vectors, all of them. In the one-dimensional case, it's particularly easy because it just means consider the left and right derivative at that point, which makes sense. This is not differentiable there. Consider those two extremes. Okay? So this is the general definition. This is the special case. The nice thing is that we basically, when we have to do computation, we're actually going to resort to this guy here. So we'll never have to deal with, this is just to understand what's going on, but we actually just going to use this when we have to actually do computations. Because the typical position, rules for gradient, like chain rule and sum rule and so on, would basically hold. Again, albeit they will need a justification that we're not going to give. Okay, so this is the first definition we did. Rather than gradient, we introduced this subgradient. Now that we have this definition, and again, I hope that this is intuitive enough that you see a bit what's going on, we actually consider two properties of this. The first one is the critical points or minimizer can be characterized this way. Okay, what do you mean? Typically, when you want to say find the minimum, you set the gradient to 0. Here, it doesn't really make sense because you don't have a vector and you can say it's 0. So you're going to say that the 0 belongs to this. And again, I hope that for most everybody, now this makes sense once you see this picture, because what is he saying is just that, at some point you get this. It means that you go from this side to this side, and so that is intuitively the condition that should give you a minimum. Okay, does it make sense? So you go from this to this, or anyway, at some point you go flat, and that's the point where you say. So among all the direction, I have the one that corresponds to the flat one. Okay? Yeah.
The 0 is 0.
Yes, of course, because those are vectors. Okay. So the question was, is this a vector? Yes, it is. Is a direction. Okay. It's the flat direction. So this is the first fact. It's kind of cute that we're going to use it in a minute. The second thing is that you can ask, okay, do I have an iteration that is a bit similar to this? An iteration where I can just, do some kind of update, iteratively update? My answer is yes. Okay. And basically, what do? You just say, I do the same thing, and whenever I'm at the point, I'm going to consider one of the vector in that direction. Okay. And clearly, you can see that there is a difficulty here, which is which one do you select and how do you compute it? Because you don't have just one direction. You have many possible ones, okay? Order is that we're actually going to consider, essentially, we're just going to select one. And the way we're going to use it is basically by considering the left derivative of the loss function, okay? I'm going to show you in a minute. But in some sense, we use a lazy, naive way of selecting one guy, okay? So this iteration is actually ensured to converge to the minimizer of this function. So if, for example, in our case, we're going to assume that our function actually not only is convex, but it is continuous and strongly convex, okay, and coercive, the story that goes up. So the minimizer will exist and will be unique. And at this point, standard results will ensure that this iteration actually does converge to that minimizer. We pay a price for this generality from differentiable to non-differentiable function, which is that in general, this step size, the learning rate, won't be a constant. It will be a decaying sequence, okay? And typically, 1 over square root of t, say, is what you could use. More precisely, it has to be something that is typically something between 1 square root of t and 1 over t, okay? It goes to 0, but not too fast. And there is a whole game of choosing that step size. So by no means this is like an in-depth discussion about this. It's just a snapshot where, again, you see that we're trying to go and use the parallel between these two things. Okay. All right. So again, this hopefully I typically do this kind of summary at the beginning of one class because we go quite a bit on material, and usually in past years it shows that doing a bit of a recap affects things in order for the second time you see it. Okay. I try to keep it in the first 25 minutes of the class. Now, this is actually pretty useful because now we can jump in and study this, and we're going to spend the next half an hour or so doing that. Okay, the first thing we want to do is that we want to consider the optimality condition. The second thing we want to do is that we actually consider the subgradient method for that loss function. Before we jump into this, so we're going to close our interlude about subgradient methods and the notion of self-differential and move to hinge laws. But before I do that, is there any question about this? Yes? What? There's a 0. Yeah, it's one of my zeros. Lurking in the shadow. Yes? Yeah, no, sorry. I use it. So last time I used here, I put a minus here and a plus here. Today is going to be useful this, and I actually don't remember exactly now, but I remember it was useful in a minute. So I know, yeah, I don't know. So this is just the left derivative. Okay, this is one of the standard notation. I checked on Wikipedia before entering, so I can tell you for sure. This is actually one of the standard notation for the left derivative. Okay, it's annoying here because this is similar to this, but it's just left derivative of a one-dimensional function. Okay, so nothing fancy here. Left derivative, left derivative. Okay, you're gonna see in a minute that I'm gonna use that, and this is one simple symbol to. Anything else? Yeah, what about it?
Why is it OB?
It's the interval between them, right?
Ah, okay. Sorry.
I mean, this is an interval. It's the extreme of the interval, the left to the right, all of them. Anything else? I mean, you can study 2 chapters of a book on convex analysis on this, right? I'm just giving you something that if you don't want to do it, hopefully you can convince yourself it's true, okay, and use it. And the point of view is that, okay, we believe this, we want to use it, and we just have to perform some computations. All right, so the computation is annoying, and my probability of making it high. So let me try to copy myself. So I want to compute this. Above or below? Below. So I called he at lambda the functional. Is the sum of the loss function plus the norm. Wait until you want to be sure that. Wait. Oh, we don't. No, we don't. So he's asking, what is the generalization of this? I wrote it above. Okay, it's the other way around. So this is general, and this is the definition of this. This is a special case where I can do this. Okay, so in general, this is not true in more than one dimension. Okay, why did I tell you this? A, because it's useful for understanding what the hell is going on, because the first time you see this, you're like, yeah, I don't know. Two, because we're actually going to use this now. We're going to show that to compute the subgradient of that specific functional there, we will actually use this. And so we reduce the computation. The computation of this in general can be complicated. We're actually going to be reducing it to many one-dimensional questions. Okay, so that's why, in some sense, this is a nice way to go. Make sense? All right, so when I have to compute the subgradient of the regularized functional, the norm part, it's easy because it's just a squared norm, right? So all I have to worry about is the loss function and the empirical risk. So instead of doing this, let's concentrate for a minute on just this. I'm sorry, I did it, but I didn't say. We're going to do this for now again by first considering the linear case. We're going to play the same game as before. We're going to do everything for the linear case, and then same game we went that way. We're going to do everything for the linear case and just say, oh, I was joking. It's not linear. It's a feature map. And then we see what's going on. Okay? So that's why from now on, I'm just going to write W instead of F. All right. So let me write, this is what? Is 1 over n sum I1 to n 1 minus yi w xi plus. And I want to know what is this? Okay? And the idea here is, suppose that this was differentiable for a minute. Then what would you get? So let's call this thing here B. And everything which is inside is what we might call A for now. Okay? Suppose that the V was differentiable. Okay? So it's a square. Then what would you do? You have to apply, to actually do the gradient of this, we have to apply the sum rule that says, okay, go in and compute the derivative of what's inside. And then the chain rule, because you have the composition of this V plus this linear function inside. Correct? If that was the case, you would get 1 over n, sum I to n. Then the derivative inside would give you minus yi, okay, xi. And then you would get the derivative of this one-dimensional function, right? Well, now we get the subgradient of this one-dimensional function. Again, just by analogy, it's kind of what you, if I ask, okay, what do you expect? This. If subgradient works well for sum and composition, this is expect. Rather than the derivative of the loss, you get the subgradient of that. Okay? So you get the minus yi xi, and then you get that. Okay? So far, so good? I always get wonderful chances whenever I see this. But then nobody complains too much, so I only have no choice to go on. Okay? How much is the subgradient of V? Consider V, don't be fooled by the fact that I put this argument here, okay? It's just a number, right? And V is just a one-dimensional function now. Can you tell me what is the subgradient? So V of A is equal to what? Just V of A is equal to A plus, is the positive part of A. How much is the subgradient? Well, it's going to be D minus V, D plus V, because it's one dimension. Can you tell me how much this is? So if A is smaller than 0, then it's 0. If A is bigger than 0, is 1. If A is equal to 0, anything between 0 and 1. Correct? Also good? So this is a number, okay? It's a number that depends on I, the specific example I'm considering. And number here is actually a number in this set, okay? So let me just rewrite this condition where A is actually what we want, which is this quantity here. So now consider A to be equal to 1 minus yi w xi, okay? Because that's what we want to do. We want to apply this result in the specific case. So and let me just rewrite this condition. What's going to happen? A smaller than 0 is going to become what? It's going to become whether this quantity is bigger or smaller than 1, okay? So I'm going to get that any element ci, which is a number in this set, is going to be something that looks like this. It's going to be 1, 0, 1, or 0, whether yi w xi is smaller than 1, is equal than 1, is bigger than 1. So I go away so that you can see. And check if I made mistakes. So this is simple. Now we have to specialize this to the case where we want to just reinterpret this in the case where the variable a is what we want, which is this. So we don't have just one a. We have many a's. We call them ci, one per example. And we just write what ci is. Ci is a number that is is in this range, okay? So notice, this condition here, now you can interpret them. What do they mean? They mean if the point is correct, not only correct, it's correct by a bit. It's not only that, you remember, this is I'm checking whether it's positive, but a bit more. I'm checking if it's positive enough. I use 1 as my enough, large enough. Then these coefficients will be 0. If it's right on 1 or smaller, then the coefficient might be different from 0. Correct? Heard that for a little bit. Yes, give me 1 second. Yeah.
You say that at 1, it's 1 over 2. Or 0.
No, I'm taking the whole interval. It's a set.
No, but then you said that.
I'm going to say it in a minute because I will need to run an algorithm, okay? So to run an algorithm, I have to do what you said. And I could ask you, why 1 up? I could choose something else. We're actually going to take always this side. You'll see in a minute. But essentially, if you ask me what is the subgradient, that's what it is. If you ask me select one element, then we can discuss which one. And we're going to see later. And you'll just see that I choose one which is simple. But for now, I want to keep them all because I want to look at them. Correct? Is the computation clear? What you should see now that this is why I said this pays off, because basically, again, up to that you have to believe that the chain rule and sum rule work the same way. You just have to compute the subgradient of a real valued function, and this is simple, and we just did it. And we just did it in 2 steps to not make the notation heavy right away. Okay? Just this is a fact. We just computed a subgradient. Now we want to see the implication of that calculation. Now, the first thing we want to do is to say, okay, fair enough. Let's check the optimality condition. What is the optimality condition? That 0 has to belong to the subgradient at W. I said that W is a minimizer if it satisfies this. Well, but now I know that this thing here are vectors of this form. 1 over n sum minus yi xi ci, where ci are those. Okay, so this is not one vector. Okay? It's many vectors depending on the ci's. Plus, I still have to put the subgradient of the norm. But that's easy because it's just the usual gradient. And this notation, it might be a bit confusing because, you know, here I have a set of vectors. I have all possible vectors like this, and here I have one specific one. You're just taking each one of the set, and you just add this element, okay? It's the obvious thing that this should mean. And so basically, I mean that there is at least one vector that for which I can realize the 0 in this way. So basically, it means that there is at least a set of that actually realize the 0. This is another way of saying it. 0 is in that set if I can do this. Okay? So now this is just a linear equation. It's not a linear equation because W also appears here, but I can at least write W, and I get a W equal, write it like this, 1i from 1 to n, xi, and then I have to write everything else. So this is going to be yi ci divided by 2 lambda. Is it clear what I just did? I just said if a ci is minimizer, if there is a direction which is good, it must realize the 0. So I can just write down how the w's that correspond, how are the vectors in that set they look like, and they must look like this.
Is there a...
Yes, and a minus. Yes, you're right. Okay? So the minus goes away because I moved to the other side, but I still have this 1 over n that I forgot because that's what I do. So far, so good? Okay, now we are using it, and we can check, okay, what is this? If you now were to take not w, but f of x, which is now wx, what kind of name would we give to this guy? Well, we just showed that this is a linear combination for some a of the training set points, which means this w, the one that solves an SVM and a hinge loss problem, satisfies the represent. We found yet again another form of the representer theorem, because look, my w satisfies this, which means that my f satisfies this. So we actually derive, as you might expect, we take something, set the derivative equal to 0, we get optimality condition, and we get another representer theorem. Okay? Yes?
Sorry, CI?
Yes, so this is a complicated nonlinear equation, okay? So what he's saying is that, strictly speaking, this CW, if you want, we can write it here too, depends on W, okay? So this defines a complicated nonlinear equation, okay? This might not be easy, no, it might not be easy to solve, but you know that the W satisfies this, okay? It's true. Then you can maybe stop and say, the story that you always want to prove representer theorem is getting annoying. So why did we show this one version? Well, because you actually learned something. You learned that not only you have a representer theorem, but you have a representer theorem where you have a specific interpretation of the coefficients. Remember the general one. The general one said f lambda x equals some k xxi ci, or, you know, yeah, whatever, ci, I from 1 to n. Here I found again the same thing, but what did I get? That I can tell you a priori that some of, that it's possible a lot of the CIs are going to be 0. Why? We just have to stare at the furthest possible corner of the board. Because that says that these CIs are going to be different from 0, either if I'm on the wrong side or if I'm on the right side, but not too much. So the typical picture you want to do is something where you say, look, let's do the one-dimensional one first. This is x, okay? This is one line. And then I basically have to check. If suppose that here, no. So I have class like this. I put a line, okay? This is my training set, okay? Then, you know, I could put a cross here. This is a wrong point. Or put a cross here. This is a wrong point, but closer. Okay, again, so this is just set f of x equals 0. Okay, so there is a plane coming out of here, and then I'm checking that. And what is the interpretation of that? Well, if I'm on the right side, if I cross here, it's fine. Okay, as long as it is fine enough. Okay, So this would basically be the distance 1 boundary. The condition over there can be just interpreted this way. Not only I'm correct, but I'm correct by a bit. So if a point is correct by 1, by a margin 1, then the coefficients are going to be zeros. If it's correct but not wrong, the coefficients are going to matter. These methods are called SuperVectors methods because they don't depend on all the training set points, but only a subset of them, and that's what we call the SuperVectors, okay? And what are they? They just come out of the fact that because we set this kind of derivative equal to 0, and this derivative has a whole set of values, this subderivative, a whole set of values, when it can be 0, we get this sparsity effect. Not all the training set might appear in our decomposition, only the ones that are either wrong or correct by not too much. Okay? So we compute. Let's just a recap, and while you think why this doesn't make sense or does. We computed the gradient, the subgradient of the empirical error, just realizing that all we have to deal with is one-dimensional functions. So it's easy, left and right derivatives. We looked at it. Then we, first thing, check the optimality condition. And we realized the optimality condition leads to another version of the representer theorem, which is kind of a more quantitative version, because it tells us that the coefficient will be 0. And in fact, whenever a point is correctly classified by a bit, it won't appear in our expansion. And this is something that you might want to use. And a lot of solvers of this kind of method try to actually exploit this property. Okay? It's just the scaling won't matter, essentially. So what he's asking is why I put the distance 1, because you're going to take the sign. When you classify, you're going to take the sign. And so it actually doesn't matter as long as, there is, you can always normalize so that this can be seen as the distance. Yeah. Yeah. I mean, we're not ignoring it, right? We're saying if you, I'm just saying pick W, okay? And W is going to define the function, correct? So I'm God, and I give you a W, okay? Then you can get the function, and you have the data, okay? And then you can check which points are correct, which points are wrong, and which points are correct but too close to 0, okay? Then I get this W, and it turns out that he has to satisfy a nonlinear equation like this, okay? But I already can tell you a priori that the CIW that correspond to i's, that correspond to point that are correctly classified by a bit will be 0. This is not an algorithm, okay? I'm just checking optimality condition. When you check optimality condition, like the logistic loss, sometimes you get something out of it, sometimes you don't. Here you get something in between. You don't get an algorithm, but you do get information about these kind of methods. And this is the reason why these methods are called supervectors. So we do this because you see why something like this might be called. Why don't we call this the hinge loss method? Because of that, okay? Historically, it's called supervector machine because of that property. And you discover it by doing this calculation. We don't have an algorithm yet, okay? That's the one thing to keep in mind. We just set a gradient equal to 0 and realize a property, but we still don't know how to compute the CIW, and it might be complicated. Okay? Or correctly, but not by much. Exactly. We discovered that this thing can be sparse, in the sense not all points matter, and the ones that matter are going to call supervectors. Exactly that. Okay? So we go this way. We could omit this, okay? We could omit this direction in our discussion, but we will never know why this method is called supervectors, and this is why it is, okay? And this is it's arguably a shorter and different derivation of this than the classical one. The classic derivation take that equation over there, and rather than computing the subderivatives, he actually introduced the dual problem. And then you have to look at the Lagrangian formulation, set dual condition, and then Karish-Kuhn-Tucker condition. It's not much more complicated, but I think the step between knowing what a derivative is and doing this calculation is shorter, because all I did is using the analogy between subdifferential and derivative. So in some sense, this is more elementary. I don't need to introduce, I kind of did introduce duality in these guys, but I argue that this is not as hard as just introducing duality in full generality. Okay. So that's it. So this is we rederived the optimality condition, for those of you who have seen it before, a la Karish-Kuhn-Tucker, just from setting subdifferential to 0, okay, or checking that the 0 is that subdifferential more precisely. One thing that you would have, if you've seen SVM before, and I guess you should have if you've seen another course before, because one of the things that typically is taught, you see that once you go to the dual formulation, you can actually prove that the minimization problem is actually equivalent to a dual problem, which is a quadratic programming problem. Okay, and that's the classical way this thing has been taught forever. It turns out that that quadratic programming problem typically is a bit heavy to solve, especially in high dimension. And that's why recently a popular way to deal with SVM-like algorithm is actually been to look at first-order method again. And so what you need to do is actually just say this. But we're in a good position to do this, because now we have some way to select a specific element of the subdifferential. But before I move that, because a bunch of you are doing like this, is there any question? Yes. No, it gives 0 weights to the point it gets correctly. The point is correct. Look, forget about the math. It's very intuitive, right? It looks like a property you might want. If a point is correct, I don't care about it. It's correct. If a point is wrong, I might adjust my solution because I'm getting it wrong. And here it's doing that, but it's actually saying, well, if it's close to being wrong, I might as well adjust my solution a bit. Why? Again, intuitively, the reason is that you're not centering this as 0. If you remember, our loss function looks like this. This is the way of doing things, and this is the way this loss function works. Okay, so I'm not just looking at 0. I basically decide that I start to pay error at 1, and this is another way of this fact to manifest itself. Does that make sense? Yes. No, it's always, yes, it's always, okay? So if you want CIs here, any of these CIs is a placeholder for a class of numbers, okay? Any of these CIs is a CIW, and whenever you see CIW, it's not a number, is potentially many numbers. It depends on W. I can just tell you a priori which number you're going to get in some cases, okay? So CI stays in an interval. And whenever you pick a W and a point, you see from there, the rule is whenever I give you Y, Xi, and W, you can tell me how much this is, right? But then it's a number that I don't know, and I will have to compute it. What I told you, though, is that if the point is correctly classified by a bit, by 1, then I can tell you that this is exactly 0. So I'm telling you, whenever you are in this condition, which you can interpret, you're on the right side by a bit. So you're not only in the right side by a bit, then this guy is going to be 0. Every other time, you have to worry how to compute it, because there is one thing to compute, and you give it a name. You call it a SuperVectors, and that's all. That's all I'm saying. Methods are called SuperVectors because there is a distinction between points that do appear in the expansion and points that do not appear in the expansion. Okay. I'm not telling you how it is when it is in derivative. I'm telling you that if it's there, I call it a SuperVectors. Otherwise, I don't call it because it's 0. Okay. Yet again, the interpretation is not new if you've seen supervector machines before. I just derived it in a different way, okay? So I don't want to spend ages explaining what this means, because I just, just the box constraint of supervector machines. All I did is show you how you can derive this from arguably a slightly more elementary argument, which is just compute derivative and check that 0 is inside, okay? That's all. Okay? More or less. Let's see, what should I delete? We're basically done, because all I want to do now is to pick one element of the gradient and write down the subgradient. And the cute thing is that you get something that is similar to what is called the perceptron. So look, I want to do the following. I want to write this method, wt plus 1 equal wt minus gamma s of omega t. But I want to tell you one specific way of picking up an element of the subgradient. So I want to use, so s omega t is going to be in the subgradient of at lambda omega t. But I want to tell you exactly how I select one, okay? And we already know that they're all, and that's what you've been complaining up to now, that they're all going to have this form, but this CI can be complicated stuff. Well, let me write exactly what I want to get. I want to get the following. S omega t is going to be I'm basically considering the left derivative. I'm just considering the left derivative of the loss function. And the left derivative of the loss function is either 0 or 1. Okay? I don't get an interval. The left derivative is a number. It's either 0 and then it becomes 1. Okay? When does it become 1? Where I have a change around 1 of this value. So that's it. Now I can run my, oh, sorry, I forgot the plus lambda, plus 2 lambda wt. Okay, that's always there. This is the subgradient. I have to worry about the selection of the subgradient of the empirical risk. The other guy is there, and it's simple. Okay. Complaints. And now look, this is now if I just don't let me repeat. You just have to plug this in this expression. It's a real algorithm now. You start from a w, okay? Then you're gonna go check expression. So here you just have w. Here what you do, you get, sorry, there is a wt. You get wt. You check whether you have yi xi. You check what is that number. It's going to be either 0 or 1, and then you sum up all this stuff, and that's fine. It's something you can do. Okay? You take that, you plug it in there, boom, you have an algorithm. Again, let's say 0. Okay? And then this is like gradient descent. It's like part of standard results in optimization theory. Typically, if you, in this case, 0 turns out to be a good choice. Okay, the result that shows that this converge typically quantify exactly the price you pay by choosing different initialization. Okay, also good. Again, this is a simple algorithm. It's just a primal algorithm. You just have to do matrix-matrix multiplication. It's very easy. Okay. When you scale up things, this is the way to go. I want to do a few comments, but I want to get close. I want to try to end this. So before I make comments, is there any question about this? It's kind of easy at this point. We computed the gradient. We just select one. And what I'm doing is that because I've selected just one of the elements, I take the left derivative. And this is what it gives me. Okay, so you see now where I commit to one choice. Here. Why? It's easy. Okay, I don't pick anything in the interval. I just pick one guy there, the left derivative. That's it. Or the lazy subgradient or something like that. Okay. Probably. Here, right? Yeah. Yeah, I'm missing 1 over n. The rest should be fine. Okay. It's very hot in here. So 2 comments. One thing we're going to skip because we don't have time, but it's exactly the same as in the logistic case, is that you can prove a representer theorem for this iteration. Again, same story as before. I could do the representer theorem. I can plug for the minimizer. I can plug it in the problem, and I can do subgradient on the new minimization problem on the C. Or I can use the same argument before. Consider the linear case, rewrite the representer theorem, prove by induction to show that this iteration itself, when subgradient it looks like this, does satisfy a representer theorem, and use that. Okay? You can do is exactly the same. So we're going to skip it. So you can prove a representer theorem, and at that point you can do this for any, not for the linear, you can drop the linear model assumption, you can do the linear function, and you can just consider any arbitrary kernel just by considering feature map. Okay? So a few remarks. The first, you can do representer theorem for subgradient method. You can do general feature map. And these two things are the same structure and reasoning of logistic loss. Okay? So if you follow that, this is the same, exactly the same. I told you that this is almost the perceptron. Okay? If you are familiar with the perceptron, suppose that you take lambda equal to 0, so you don't regularize. And suppose also that you change the loss function so that rather than having this form 1 minus yfx, you actually take away this y. What will be the effect on the algorithm is that you're going to check this value against 0 rather than against 1. So you don't keep this margin. Okay? Then this would be a batch perceptron. It's exactly what it is. Okay? What you do is that you check points, and whether they're correct or wrong, you decide whether you want to update things or not. Here, to wait, you're going to wait to check all the points before you update. The perceptron is the stochastic subgradient version of this. So what you do, rather than using this, you would actually use just, you get a point, you check the value of this quantity on that one point, and then you update. Okay? So again, I'm not going to write it down because it takes more than what I want to spend on this, but basically if you take lambda equal to 0 and you replace 1 by 0, then this is a batch version of the perceptron. If rather than subgradient you consider the stochastic version, the one where rather than waiting to see all the points and compute the subgradient of all the points, just compute the subgradient at one point, which usually means just delete this xi, yi. This is the perceptron. Okay? So this, if you want, what we just, the subgradient method for SVM, for hinge loss, it's the regularized with margin batch version of the subgradient. So you do batch, you add regularization, and you add a little margin. Okay? And then you go from perceptron to subgradient SVM. Okay, what about class you've probably seen if you've ever seen SVM before. Why do we go this way? Do we gain something? Do we lose something? Why do we get this presentation? The classical way to go through SVM is from a modeling perspective, is rather than just saying, oh, it's a loss function, and then is a Tikhonov regularization, you actually give a ad hoc derivation that is based on this picture. You introduce the geometric margin, and you go that way. You first start to say that things are linearly separable. Then you actually say that they're not really. Then you make nonlinear. And then at some point, that argument is kind of cute, but they become a bit hard to control, especially in the nonlinear, non-separable case. You're like, yeah, you're cheating. It doesn't quite work. And if you want, this is one way to say, well, okay, but you can go that way if you to go bottom up. Otherwise, you can just derive it from this. So you've probably seen it the other way. So now we just derive it from this. And I think in 2017, arguably, this might be a way to go, okay? Just because you see that it's just a special instance of a general thing that you can do another way. So that's one primary difference between other representation of SVMs. The second thing is, once you have to do computation and derive the properties of the method, typically the way you do is that you stick to this, introduce duality, write a Lagrangian, spend 3/4 of an hour doing derivatives, then typically believing duality and duality theory, derive an algorithm that is a quadratic programming problem, then you don't know how to solve it anyway. And then you find that you do have this notion of supervectors, okay? I like this way better, again, in 2017, because time has passed, because rather than duality, you introduce the subgradient. Of course, it's also new information, but it's somewhat more intuitive than, at least to me, so it's a bit of a biased choice, than going through duality. Again, it's like baby duality, okay? It's not like I'm cheating a bit. I'm just simplifying things a bit. And then what can I get is the notion of supervectors, but just by checking optimality condition, which is arguably something a bit more intuitive. And then rather than go and solve the quadratic programming problem that you don't know, you lose in touch with algorithm right away, we go this way and we just introduce simple subgradient. I argue that actually this is the way typically things go when you have to deal with high-dimensional problem. You try to stick to these kind of techniques. Did we lose something in going this way? Well, what we lost is that this one algorithm that I show you might not preserve sparsity of the solution. Because of the specific way we set up the problem, one can check that once you write down this, you may lose the sparsity of the solution. Okay? The sparsity in this sense, the fact that some of the CIs are going to be 0, can be exploited by solvers that use quadratic programming techniques. Typically, when you compute this, what happens is that once you make a mistake, this is going to affect all the coefficients. They're not going to be 0. So we lost the sparsity of the solution. It takes a while to see this, but this is what happens here. So should you care a lot? Well, in practice, people don't care that much in a lot of application because sparsity is not a factor in order of magnitude. Okay, the number of 0 points there, especially in high dimension, is not huge. This picture is definitely misleading because it's a two-dimensional picture. So it looks like there are very few things close to this, and most of them are far away. If you take the same picture in 10,000 dimension, which is kind of hard to do, but typically everything is close to everything. Okay, and most things are supervectors. You don't really have, you might have a factor 2 or 3 of points that are not supervectors, but it's like 10 or 100. So you don't get order of magnitudes improvement from that. You just get factors. And so at that point, oftentimes using things like this actually do provide something more efficient. Okay? Yes? So each iteration costs less. I mean, I don't know, because quadratic programming is not an algorithm, it's a problem, right? So you have to discuss what kind of solver you want to use. So he's asking about how do you compare the two things. It's not so easy because this is an algorithm in the optimization sense. Quadratic programming is a problem in the optimization sense. Then you have to solve it, and you have to tell me how you want to solve it. You want to solve it by interior point method, you want to solve it by, whatever method you have. I would typically say that the kind of method you can use for quadratic programming problem are typically faster, and they can typically exploit the sparsity, but they might be heavier from a memory point of view. Okay. In large-scale scenarios, things like these are used exactly for the reason I told you before, because you just multiply stuff. Yeah. Of the? Yeah, of course, because this is just subgradient method. Subgradient method, optimization. It's one of the most classical method. And again, it's like subgradient. This is by far not the best thing you can do. You can try to do something smarter. You can try to accelerate by the step size, do it stochastic, but yeah, absolutely yes. And this is not super fast. Again, it's like gradient descent. It's a bit of a simple choice, okay? But conceptually, this is the starting point. Then you can be fancier, but it's another course. It's a course about fast first-order methods. Okay? More to say? Yep. For the 50%, local minima, global minima, perceptron. Can you fill in the gaps? Can you tell me whatever else you said? No, I actually don't, because that's kind of a complicated problem, because look, this method here is the convergence of this guy. It's easy because anyway, I'm regularizing. There is this term, and this means that I'm actually solving this problem. So I'm actually starting from a problem. So the method, when you use this method that I gave you, plug this expression in here, this is a method to solve this problem. And this problem is strongly convex. okay? And so to study the convergence of this, I'm doing it for a strongly convex problem. When I go to perceptron, not only I'm changing the algorithm, I'm actually changing because I'm basically taking lambda equal to 0. And I'm taking the 1 away. The 1 away is not such a big deal, but the W away makes life a bit harder, okay? It's not too hard. It's still convex, but it's not strongly convex, so definitely you're going to get a worse result. It's still one case. The classical result about perceptron don't go the optimization way. They really go more of a learning way, and they say, what if my data are separable? Can I get the rate of conversion that depends on how nice is my data set? It's kind of a very nice idea, but have you ever seen that done in optimization? No, because they don't even know what you're trying to classify. They just try to minimize something. When you take the optimization point of view, you just try to solve the problem like that. You don't worry about classification error. You just try to get an objective function small. Okay. Anything else? Okay, so this is the 9520 version of SVM. Or 6680, that way. What do we want to do next? We're almost done. 1, 2, 3. That's my favorite, least squares. You guys do this often, right? You wait and then yeah.
Well, the thing is, we said let's discuss.
Yeah.
So we put one.
I chose it equal to 10. No, lambda goes to 0. I mean, look, the problem is more complicated than that, right? I mean, here everything is fixed. The data is fixed, and I'm not worrying. Lambda will never go to 0 unless n goes to infinity. And when n goes to infinity, okay, I don't need to worry about computing things, for example, because I put my statistician hat, and I don't care about computers. I just care about it's optimal in this sense, okay? So absolutely, you're right, but that's misleading. You're not going to go this. This is an equation that I wrote to emphasize computations and learn something about it, and using logistic regression is going to excuse to go here and make things somewhat simpler. Again, this is complicated the first time you see it because you've seen it in another way, but if you have to see this for the first time, it's much simpler than the other way, okay? Because it's just like logistic regression. The question about lambda going to 0 appears when you don't even worry about this. You just say, okay, what happens if lambda goes to 0? And let's assume that I do get the minimizer, okay? So it's an interesting question, but somewhat separate from the discussion up to now. Okay, now I delete, but you can stop me. Okay, so let's try to give a highlight of the main things, and we're going to continue next class because we're still going to do least squares, but in a slightly different way. So we want to do this, and we're going to play the same game we did before. We're going to start from models and understand what's going on for there, and then we keep on going. And in this case, this loss function is smooth, so we're going to get the gradient and set it equal to 0. But before doing that, we actually change notation a little bit because this is nice to write in vectorial form. So for this specific choice, lambda, which now becomes a function of w, can be written just this way: 1 over n sum x w minus y square plus lambda w square. So this is the data matrix, which is n by d, and this is the output vector, which is n by 1. Agree? Just comes in handy to do this. Then what do? We just take, is this fine? Go silent, so it means yes. And you do the gradient. Might guess that I've done this a couple of times in my life. this is just a composite function of a square, so it's twice. You just have dealing with the vector k, so you get X transpose here, you get that equal to 0, and boom. You know, just as a side note, you just realize why people love squares, because whenever you see squares, you get linear stuff when you take derivatives, and then computation become easy. So here we put a square here and a square here, because then we just get the linear equation. And so we get transpose. The 2 doesn't matter. We get X transpose X plus lambda. I take this n and I put it in front of the lambda. And I found out that the unique W that satisfies my strongly convex problem can actually be written this way. Okay? There are two things that are nice about this. One is that, again, we can prove a specialized version of the representer theorem in one line, and I'm going to just write it down. This gives rise to a linear algebra interpretation of whatever we're doing, okay? Because here we're just trying to invert matrices. So we're going to discuss this at length next class, too. So let me just give you the form of the representer theorem, because it's very easy, okay? Yes?
What is that y hat?
Well, what?
Y hat.
It's just a collection of all the y's. So X is the matrix where in each row I have one element of the training set, x1, xn. So it's n rows, d columns. Y hat is just a vector with y1, yn. Okay? Fine, all right? I want to do the linear kernel version of the representer theorem, okay? Which means that I want to show that the W, let's call this guy W lambda, okay? Is the minimizer, is the one that satisfies this equation. I want to the W lambda that satisfies that equation can actually be written this way for some C, which again means that this is written this way. Which again means that f of x is equal to sum x xi ci, okay? If I'm doing linear functions. So I want to prove this. I want to prove that there is a C for which, let me call it C lambda, that satisfies that equation. If I pick W lambda that way, I can also write it as X transport for some C. Okay? It's the C I've been playing now for 3-4 times. Okay? How do you prove that that W satisfies this equation? Well, let's check. W lambda is equal to X hat transpose X hat plus lambda n I to the -1 X hat transpose Y. Right? I just took I did the inversion of the matrix, which is invertible because I have a symmetrically positive definite matrix, and then I get something added on the diagonal, and this makes it invertible. And if you don't remember that, we're going to discuss it for like 2 hours in the next. So this is fine, okay? Okay, let me tell you the answer, and you tell me, is Jeopardy. I tell you the answer, and you tell me how to do it. So this is true. So this is true. Why? So let me show you what I did. I took this X transpose, and in some sense, I moved it in front of the parenthesis. And then I have to swap the order inside, otherwise dimension-wise it doesn't work. And maybe I should put a transpose here. Okay? Okay. That doesn't sound legal, is it? Yes. How do you show it? Well, there are many ways. One simple SVD. Okay? So just take the SVD of this matrix. U sigma V transpose. Whichever compact way you want to use to write it down. Now plug this expression here, plus this expression here. It's fine. Okay? You get an identity. You check that way. Okay? It's a general fact that this is true, and you can just check by SVD. We're not going to do it. It's literally, there's nothing interesting in this. You just have to go in and delete a bunch of orthogonal matrices, and you get an identity, period. SVD. Why am I happy? Well, because how big is this matrix? So this guy is n by d, then this guy is d by n, so this whole thing is n by n. This is n by 1. So this is a legitimate choice for my c lambda. This is actually c lambda. Okay? It's fine, it's c lambda. What is this matrix? How does a single entry of this matrix look like? So if I write down x transpose I, say ij, how does it look like? Okay, the first column the first row times the second column. What is it?
Inner product of it.
Right, it's the inner product of xi and xj. And remember, these are the training set points. So that's actually the linear kernel between 2 points. Correct? This is what we call the empirical kernel matrix. Is the kernel matrix that I obtain by evaluating the kernel on the training set points in the linear case. Okay? Now, how does this story translate if we go to the nonlinear case? Well, I would have to replace whenever, again, in the linear case, you have to do the game you did before. Whenever you see x, you have to do phi of x. Formally, you can write w, but w becomes an infinite dimensional object. But c is still a vector of dimension n, independently of the size of the vector. So you're going to get that this expression is now replaced by this expression. And this expression is going to be replaced by this expression. Well, you tell me. What should I write inside of here? Instead of the linear kernel, I want to use a generic kernel. For the linear kernel, I get this matrix. Guess what? If I don't use the linear kernel, but I replace this with a feature map, this becomes what? Well, this becomes phi xi, phi xj. But this is what? The kernel matrix. Okay, so it's the kernel. So this is k xi xj. So define k hat to be the matrix with the entry ij equal to this. This is what I have to write here. Okay. So least squares computation are particularly easy. You set the derivative equal to 0. You get the linear system. Now, again, you could go back the usual way. You take the first representer theorem, you plug it in the function, and you take the derivative with respect to c. Here we go another way. We try to find out that the w that satisfies the system is this. They turn out to be equivalent in this case. Okay. How do you prove the representer theorem? Well, you just go for the linear case first. You swap the order of the matrices, and you see that now all you have to do is to invert a regularized version of the empirical kernel matrix on the data. That settles it for the linear case. And then you just do the kernel trick. Okay? You just take x and you say, I'm going to replace it with phi x. Then this expression becomes this. And the c lambda expression becomes this. And that's it. Okay? So amazingly, we managed almost on time. This was a bit quick, so we're going to discuss it again. But again, the goal of the next class is basically to expand on this, showing how this point of view is actually very useful because it suggests a different way to design learning algorithm, which is not Tikhonov regularization. It's something completely different. We'll see that whenever you project your data, you can probably think of that as a form of regularization. Whenever you optimize something on your data, optimization itself is going to be a form of regularization. Okay? And this is really different from what is usually done. That's it.